Circular Motion
and Gravitation
by Bierman
and Wilmer Reynoso.
Circular motion and gravitation. A pendulum is a weight suspended from a pivot so that it can swing freely. A pendulum starts with the highest potential energy at its highest point and the highest kinetic energy at its lowest point.
Here's your problem. A tire swing has a period of 2.5 seconds. How long is the swing here on Earth? If the swing was taken to Mars, where gravity is 1.6 meters over second squared, what would the new period be? Here's a picture of the tire swing on Mars. Here's a picture of a tire swing on Earth. These are some of the variables that we'll be using to solve our problem. T, L, G, and pi. T is period, L is length, G is gravity, and pi is pi. The units for T are seconds, the units for length are meters, the units for gravity are meters over second squared, which is 9.8 meters over second squared on Earth. And the units for pi are non-existent because pi doesn't have any units. Here's the formula we'll be using to solve this problem. Period equals 2 pi times the square root of length over gravity. First, we'll state our givens. We'll refer back to our problem to figure out our givens. Our first given is the period, which is 2.5 seconds. As said in the problem, a tire swing has a period of 2.5 seconds. So period equals 2.5 seconds. We'll put S for short. Our second given, although not stated in the problem directly, is our gravity, which is 9.8 meters over second squared since we're talking about a tire swing on Earth. So gravity equals 9.8 meters over seconds squared. Since we have period and gravity down, the only variable left is length, which is what we'll be solving for in this problem. We'll put a question mark for length. So length equals question mark. The next step will be plugging in our givens into our formula. So that would be 2.5 for T. Then we'll do 2 times pi, which will be 6.28. Then we put times the square root of L over 9.8. Next, we'll divide 2.5 by 6.28. This will give us 0.398 equals the square root of L over 9.8. 6.28 cancels out. In order to get rid of the square root, we'll square both sides. .398 squared will give us 0.158. Then we'll put equals L over 9.8. The square cancels out the square root, so we're left with only L over 9.8. Next, to get L by itself, we'll multiply both sides by 9.8. This will give us 1.55 meters as our length on planet Earth. That's the first part of our problem. The second part, we're taking the swing to Mars. where gravity is 1.6 meters over second squared. The only difference is just changing the gravity in the formula. So let's do this one more time. For t, we'll put 2.5. 2 times pi is 6.28. Then we'll do times the square root of L, not 9.8, but 1.6. Now we'll do the same. So we have 2.5 divided by 6.28. This leaves us with 0.398 squared equals length over 1.6 squared. 0.398 squared equals 0.158. The square and the square root here cancel out, so we're left with L over 1.6. To get L by itself, we'll multiply both sides by 1.6. This will give us 0.253 m as our length for the tire swing on Mars. So, in conclusion, we have 1.55 meters for our length on planet Earth of the tire swing, which is our pendulum. On Mars, we have 0.253 meters as our length for the tire swing, which is our pendulum on Mars. The only difference between these two parts of the problem is that the gravities are different. The rest is just the same formula, just being used in a different way. This is our rundown of circular motion and gravitation by Bierman and Wilmer Reynoso.